Assalamu alaikum everyone. So lecture number 2, and we will be discussing more number systems and complements, right? So last time we discussed binary, decimal, octal number systems. What we did not discuss hexadecimal numbers, right? So today we will be discussing about hexadecimal numbers, right? And then we will be having more examples regarding the conversion between hexadecimal, octal and binary number systems, right? And we will be having more examples, right? Because these concepts, they are very important, right? When we will be talking about the design and the number system and their interconversions, right? And then the range of values, right? So one of the problems which we come across, that on a piece of paper it's easy to represent a negative number, right? So normally what we do whenever we have to write down a negative number, right? So we put a bar on the side of that number, so it indicates the negative number, right? So but if you talk about the computer design, computer system, right, or number system, so this is not the way out, right? So you have to handle this negative number representation in another way, right? So for that, what we need to complement, right? Take the complement of those numbers, and after the complementing the numbers, we can add, we can perform certain operations that includes addition and so on and so forth, right? And that finally that will remain with us via binary, right? Okay, so here binary number systems, they are made of binary digits, right? So we have taken BI from binary and IT from digits, so we have declared it bits, right? 0 and 1, 2 bits. So again here we can have an example, right? So these are the this is the binary number, and we have to convert that binary number into an octal number, right? So you can see that we have 4-bit binary number. This is representing the base, right? And what normally we do, right? We have already converted number like that, so I'm placing those at a distance: 2 raised power 0, 2 raised power 1, 2 raised power 2, and 2 raised power 3, right? So this is what 2, 1, right? So this is 1, 2, 4 and 8, right? So 8 plus 0 plus 1 plus 1, right? So this is 2, this is 11, right? So we will place the base. So here how we have this, right? 1 1 0, base 2, right? So let me write down like this: 1 1 0 0.1 0, 2 raised to power 0, 2 raised to power 1, and 2 raised to power 2, right? So the difference is, right, so as I move from right to left, I will be raising the 2's power, right? So after the fraction, when I will move from left to right, I will raise the negative parts, right? So this is what 4 plus 2 plus 0.1 by 2 plus 1 by 4, right? So we can have the answer, right? 1 by 2.5 and 1 by 4 right? So it is 0.25, right? So 0.25 and then 0.5, not 0.5, 0.5, right? So 5 and 7, right? So I will be having 6.75, right? So here we have group of bits. So here we have represented hexadecimal numbers, right? So you can see that we have 0, 1, 2, 3 till 9 we have the same, and after 9 this is 10, 11, 12, 13, 14, 15, right? So here is the conversion, right, from hexa to decimal, right? So how I will be doing this: 3A 9F, right? And it has a base of 16, right? So I will be having, right? So let me place like this: A 9F, right? So it's hex 16 raised power 0, 16 raised power 1, 16 raised power 2, and 16 raised power 3, right? So 1, 16, right? 256, right? And you can calculate this, right? So I will be having 16 raised power 3 into 3 plus 256 into A, right? That is 10 plus 16 into 9 plus 1 into 15, right? So I will be having this is the number and base 10, right? So here we have the fraction, right? So let me solve the fraction over here. So we have 2D 3.f 16 raised power 0, 16 raised power 1, 16 raised power 2, right? So after fraction, 16 raised power minus 1, right? So 2 into 16 raised power 2, right? Or you can say 2 into 256 plus D 13, right? So here D 13 into 16 plus 3 into 1 plus 5 into 16 raised power minus 1, right? So I will be having 723.3125, right? So after I have to place the decimal point, right, or fractional point after this, right? So here is the equivalent binary representation, right? So we have numbers starting from 0 to 15, right? Total of 16. So how many bits I need in order to represent those unique binary numbers? So 0, 0, 0, 1, 1, 0, and we will continue this till we reach 1, 1, 1, right? So you can see here, right? So this is what 1, 1, 1, 0, right? So this is 8 plus 4 plus 1, right? So 13, and that is 13 is 10, 11, 12, 13, D, right? So this is the story altogether, right? Decimal, binary, octal, and hexadecimal, right? 0, 0, 0, 0, 1, decimal, 1, 1, right? So this is binary, 1, 0, right? Octal 2, right? So you will see the similarity between octal, hexadecimal, and decimal, right? So 3, 1, 1, 3 till 7, right? So here we have difference in representation, right? 8, right? So 1 0 8, right, 9 1 1 9, right. So how if I have to represent 9, right, so how I can represent 9? So this is what decimal, right. So I will be dividing by 8, right, 1, and 1 is the quotient and remainder, right. So I will be having 1 1, right. So whenever we talk about 11, right, so 8 1, and that is 3 11, so we have 1 3, right. So this is a sort of conversion. So here you can see that we have equivalent binary representation, right. So for decimal 0, right. So if I look here, for A we have 1 0 1 0, right, B 1 0 1 1, right, for F all ones, right. So ultimately what we need to do, we need to design a circuit that can convert those different number systems, right. So here because now we learned that if we have this table, right, so we can use straight away this table, right. So 3A 9F, right. So for 3 we have 0 0 1 1, right. This is 3. For A, right, that is 10, right. So 1 1 0 1 0 1 0, right, 1 0 and 1 0. 8 plus 2 10, right. For 9 we have 1 0 0 and 1, right. For F we have all ones. So you can see that each hexadecimal number is represented by 4-bit binary number, right. So in all we will be having this, right. So if we, right, so in other words, what we can do, we can convert this, right. So first of all we have to convert, because here we have converted this into the binary, right. So first we will be converting it into, if we remember, right. So here we have the number 2 base 2, right, and here we have the hexa, right, and here we have the decimal, and here we have the octal, right. So we have here, from here, right, this is here and this is, so there is no state arrow between those systems. We have to go via the base 2 number system, right. Here again another example, right. So we can also have the same, we can use the same table, right. So we have the binary equivalent for this octal number system, right. So we are utilizing the same, right. So here you can see we have 3. So the binary equivalent of 3 is 0 1 1, right. So for 5 1 0 1, right, 0 1 0, this is for 2 and 3, and this is again for 7, right. So here we have converted from base 16 to base 2, right, and then we are, right, so for 7 you can see this is 7, right. So here they have done something else, right. So what we did, we group those bits in 3s, right. So because if I talk about the octal number system, right, so let me write down here 0 0 0 0 0 1 0 1 0, right, and here we have 0 0 0 0 0 1, right? 2 and 0 1 1, that is 3 2 1 0. So here we have 1 0 0 for 4, for 5 1 0 1, for 6 1 1 0, for 7 1 1 1, right? So 7 6 and 5, right? So this is what? This is 7, right? So this one has to go here, 0 1 1 0 1 1, right? 1 1. So 0 1 1, this is 3, right? So then we have to take 0 1 0 2, right? And this is 1 0 1, right? 5, and here we have 1 1, right? 3. So 3 5 2 3 7, right? So this is the, so how we are managed to get this. We grouped those binary numbers into 3-bit each, right? So this is the first group, right? And then we have another 3 bits, right? So another 3 bits, another 3 bits, right? And another 3 bits, right? We can ignore this 0. So we are 1 2 3 4 5. So 1 2 3 4 5, right? So 5 digit octal number, right? Okay, and then here we have another example. This is very simple and we have already gone through this. So here we have the decimal to binary conversion, right? So you can see the division, right? So this is the right remainder, quotient, right? So here again division, right? So quotient, remainder, quotient. So we will move like this, right? And then we will be having, you can see that we have to start from here, right? So this is the most significant bit, right? And this is the least significant bit, right? So here what we need to do, octal to decimal, right? This is the octal number, right? And you can see that we have started from here, right? So we have started from here, right? 8 raised to power 0 1 2 3, right? So it's a sort of increasing, right? And here we have decimal to octal, right? So because targeted base is 8, so we are dividing by 8, quotient, remainder, quotient and remainder, quotient and remainder, right? So this is the answer, 5 4 7. This is most significant and this is least significant, right? So here what we did, we converted a decimal number into an octal number, right? So here binary to octal, right? So how we will be doing this, right? So we will grouping in 3, right? So this is what? This is 4 plus 1 5. This is 5, and this is what? This is 6 6 5, base 6, right? So here octal to binary, right? So we are going through a lot of different examples in order to have more practice, right? So 13 base 8 into base 2, right? So you can see that 3, right? For 3 I have 0 1 1, that is 3, right? And for 1 0 0 1, right? This is 1. So I will be having 0 0 1 0 1 1, right? So that is base 2, right? So here again this is radix 3 8, right? So what we need to do, we need to divide, right? So this is the quotient and remainder, right? Again divide by 8, quotient and remainder, right? and further it is not divisible, right? So we are left with 2322, most significant bit, and this is least significant bit, right? Octals, right? See, octal number, right? So here we have almost the same mechanism, but we have included this in animation, right? So hexadecimal, right? This is the example, right? So how we will be handling, so this is what 1100 base 2, right? So in decimal, right, it is 12, right? 8 plus 4, 12. In octal, this is what, right? This is 16, right? So for this we have 0010. For C we have right, 10, 11, 12. So this is 12, right? This is 2 and this is 6. For A we have 10, 8 plus 2, 10, right? Right? So this is the utilization of hexadecimal in computers, right? Right, so you can see the volume number, right? Volume serial number is written in hexa, 94943E, right? So this is hexa. So this is another representation, conversion binary to hexadecimal, right? So now we are given this binary number and we wish to convert that binary number into hexa, right? So here you can see that we have grouped the bits in 4, right? So 1, 2, 3, 4 groups, right? So this is what 6, 1, and this is 12, and this is 10, right? So we cannot write like this 10, 12, right? So for 10 we have A, for 12 we have C, right? And for 1 we will straight away write the 1, and for 6 we will straight away write the 6, right? So here convert this decimal into hexadecimal, right? So 16 divide by 16, right? So this is the quotient and this is the remainder, right? 16 fours are 64, right? And this is the remainder, right? So you can see that we have mentioned the remainder in hexa, right? In other words, if 64, 77, right? So we are having 13. So 10A, right? 11B, 12C, 13D, right? So we have mentioned D. So this is most significant and this is least significant, right? So base 16, right? So again here we have mentioned the animation for understanding, right? So we are having 2EA base 16, right? So 0, 1, 6, 2 multiply by 16 raised to power 2, right? Plus 14. Instead of E, we have to write the corresponding decimal, right? So 14 into multiply or multiply by 16 raised to power 1 plus this is 10, right? So this is something different, right? Because we are representing the hexadecimal numbers by their corresponding in order to have multiplication, right? So A10 multiplied by 16 raised to power 0, and we have to add them all, and this is the equivalent decimal number, right? So here we have octal to hexa, right? Right. So how we will be converting, right? So one system to the binary first, to octal, right? So what we can do, we can first convert into, right, this, right, and then from 8 is this these are the corresponding binaries, right? And then A, this is 10, right? So now after that we will be grouping them in threes, right? So this is 0 1 0 3, this one will go with those two zeros, and those two remaining bits will go with 0, and we have 1 1 1 here, right? So then we have to write down the equivalent and corresponding hexa, right? So this is 2, this is 1, and this is 2 7, right? So this is 7 2 1 2 base 8, right? So here we have to convert this to hexa, right? So we will be writing down the corresponding binary, right? So 0 1 0, right? So you can see we have 0 1 0, right? And this is for 2, for 5 1 0 1, for 7 we have 1 1 1, right? And you can see that now we have to group them in fours, right? So this is 4, again this is 4, and this is 1, right? So 1 0 1 0, and those ones, and right, 2 1s, and this is 1 0, right? So regroup in 4 bits, right? So this is what? A 10, right? So this is 8 plus 4, this is 13, right? And this is 1, right? So 1 EA with base 16, right? So here again octal to hexadecimal, right? So here we have another methodology, right? Octal, right? So 6 7 0 1, right? So we are grouping, right? So this is 4E, and this is what? Right? 3 plus 2, 2 plus 2, 3, right? So 2 zeros and 2 1s, and they are equal to 3, and we have 2 over here, right? To hexadecimal 2, right? So here again we have the same, right? So hexa to octal, right? So we have 5A, right? So 16 raised to power 0, 16 raised to power 1, right? 1 16, right? So multiply 80 plus 10 90, right? So we will be now having the division, because we need to convert that hexa. So first we have converted that into decimal, and from decimal we are converting this decimal into octal, right? So it will take 2 steps. First conversion from hexa to decimal, and then from decimal to the octal, right? So here 90, right? So this is quotient, remainder, right? Again, right? Quotient and remainder, right? Quotient and remainder, right? So 11 3, and it's not further divisible, right? So 132. So binary to decimal, right? So we are handling fractions over here, right? So 1 into raised to the power, so after the fraction, right, 2 raised to the power minus 4, 1 into 2 raised to the power minus 3, right? So we have started from here, 2 raised to the power minus 1, 2 raised to the power minus 2, 2 raised to the power minus 3, and 2 raised to the power minus 4, because we have 4 binary digits after fraction, right? So here we have the simple parts, 1 into 2 raised to the power 1, 0 into 2 raised to the power 0, right? Then decimal to binary, right? So here you can see we have 1 1, and we have the multiplication, right? As opposed to the division over here, right? Because here we are handling fraction, right? So here another example, decimal to the binary. This is radix, right? So we will be multiplying, right? So multiply by this is the answer. 1 will remain here, and this is the fraction. Fraction will go here, multiply by the radix, right? And then we have 0 integer 75 will go here, 2 multiplied, right? So 1.5, 5 will go here, and we are having 1, right? So 0.1011, right? So this is the answer. And then base 10 to 16, right? Multiply by 16, right? 8 will go here, and then the value of the fraction will go here, 16. 3 will go here, 3 to 8 will come here, right? 5, right? And 5 will go here, and 248 will go here, and we have 968, right? So what we will be having 8356, right? Right. So whenever we talk about the number system, right, any number system, so we need to represent the positive numbers as well as the negative numbers, right? So if we talk about the representation of a negative number on a piece of paper, so it's rather easier to put a bar on the side of that number, and that indicates that this number is negative, right? So on a piece of paper it's easy to represent, but whenever we talk about the computer system or some circuitry, so this is not the case, right? So what we need to do, we need to handle those signed numbers in a different way, right? So here what normally we do, we will take complements, right? So we have signed magnitude, 1's complement and 2's complement, right? So what normally we do, we reserve the leftmost bit, right, for the sign, right? So if we have a 1 here, so it means this is the sign number. If we have a 0 here, so it indicates that we have the positive number, right? So you can see that we have 12, right? So if so 8 plus 4, 12, and this bit indicates the sign is negative, right? So here this is again 12, but we have 0 here, so it means we have the positive number, right? So how we will be exploiting or using that complement, right? So as I have mentioned that whenever we want to represent a negative number on a piece of paper, it's easy, right? And we can also solve, add or subtract on a piece of paper, right? But regarding the circuitry, we cannot do that, right? And obviously we come across positive numbers and negative numbers, and we have to perform certain operations that includes addition, subtraction, and so on and so forth, right? So what we will be doing, right? So we will be taking the 2's complement of the negative number, right? So it means after taking the 2's complement, we simply have to add those numbers and we will get the resultant, right? So this is the utilization. So let's talk about an example. We have a 3-digit decimal representation, right? And we talk about we will talk about the odometer, that is normally we have in the bicycle, right? And here you can see that if we have negative, we don't have the negative sign, right? So we cannot tell plus 998 from a minus 2, right? And you cannot tell that either you move forward or you move backward, right? So how we will be handling this, right? So if for example you have 998, right, plus 998, right, or 998, so you cannot say either you move forward or you move backward, right? So how we can handle, right? So we can overcome this problem if we divide or those 3 decimal number representation into 2 chunks, right? So starting from 0 to 4 499, right? So, or you can say 001 to 499, and that we have dedicated for the positive number, right? And from 500 to 999 to represent the negative number, right? And this is the central point. You can say this is the center, and on the one side of this center we have the positive number representation, and on the other side of the center we have the negative number representation, right? So how we can handle that problem now, right? So this is not a big deal. Plus plus, right? So here we will be having the problem, right? So 006, right? So minus 3, and we can represent this minus 3, 997, right? And we can discard the carry, right? So here we have plus 3, that is the correct answer, right? So for this we have 995, right? And 002 997. Again, this is true, right? Here again, right? So this is equivalent to minus 3. So here minus 2, 998 and 997, right? So again we have to discard the carry, and it is also working, right? But the problem is, right, so it's easy to convert minus 3. You simply count down, right, backward, right, from 1000, that is 998, 998 and 997, right? So that will do the job, right? But the problem will arise whenever we have to do this for large numbers. For example, minus 218, right? So that is 786, right? So we cannot count over here, right? So we need to look for something else, right? So that's why we have introduced complement over here, right? So we will be having the tens complement process that uses the base 10 decimal number system, right? So first complement all the digits in a number, right? So digits complement is the number you add to the digit to make it equal to the largest digit, that is 9, right, in the base. The complement of 0 is 9, 1 is 8, 2 is 7, and so on and so forth. And then after that, what we need to do, we need to add 1, right? Without this step, right, our number system would have two zeros, plus 0 and minus 0, right? So that's why we add 1, right? So because we don't have a number system that represent plus 0 and minus 0, right? So these are the examples. So first we have to take the complement, right? So I have to make it a 9, 3 plus 6, 9, 0, 9. So this is the ones complement, right? So this is the ones complement, and then I have to add 1, right? So here 997, right? So this is the true representation, right? So here again the example, right? So 4 plus 5, 9, 1 plus 8, 9, and 2 plus 7. So I have to make all the bits, right? So in other words, you can say I am complementing all the bits, all the corresponding numbers, digital number digits, right? So here we have to add 1, so 786. So that is the job done, right? So this is the complement whenever we talk about the decimal number system, right? So decimal we normally talk about it's base 10, right? So if base is R, so R1 minus 1's complement, you can say in a general way, right? So 1's complement, right? And here you can see that 1's complement of this is, right? So what we need to do, we need to invert all the bits, right? So as you know that we have inversion over here, right? So this is 1's complement, and addition of 1, in order to eliminate plus 0 and minus 0 possibility, we have to add 1, right? ones complement of this is what, right? So we have to invert all the bits 0 1 1 0, right? So let me write down over here. So if I need to take the complement of 0 1 0 1 0 1 0 1, right? So 0 1 0 1 0 1 0 1, right? So I have to take the complement of each corresponding bit 1 1 0 1 0 1, right? So this is the complement of this, right? So you can see that I have taken the complement of this, right? So I will get the original number 1 0 1 0 1 0 1 0, right? So okay, right? So after taking the complement, right? So here if I have minus 12, right? So you can see that this is complement of minus 12, right? And this is sign bit, right? And then 2's complement, right? So what we need to do, right? So if I want to take the 2's complement of 0 0 1 1 0 0 1 1, right? So 0 0 1 1 0 0 1 1, right? So I will be inverting all the bits, right? This is 1's complement, right? And after addition, in order to eliminate the chance of plus 0 and minus 0, 1 0 1 1 0 0 1 1, right? See, right? So 1 1 0 0 1 1 0 1, right? So this is the 2's complement, right? So here we have the number, right? So 12, and its 2's complement represent the signed number. This is 12 and this is minus 12, right? Similarly, if this is 12 and this is minus 12, right? So one's complement. So here you can see that we have 12 and this is minus 12. Negative of 2's complement number, take the 2's complement, right? So okay, so this is the algorithm, right? So algorithm 1, simply complement each bit and then add 1, right? Least significant bit, copy all the bits up to and including the first one, right? So here we have the first one right from the start, right? So we will be complementing rest of the bits, right? So we will leave this, right? And rest of the bits has to be complemented, right? So we can verify, right? So I will be complementing this by using this algorithm 1 0 0 1 0 1, right? So I have to invert all, right? So this is 1's complement, right? After deletion we have 2's complement, 1 1 0 1 1 0 0 1, right? So 1 1 0 1 1 0 0 and 1, right? So this is 2's complement, and this is the second algorithm, and we have verified that they are the same, right? So we have two algorithms in order to compute 2's complement, right? So here we have the finite number representation, right? So now let's talk about the addition by using 1's complement, right? So here we have no sign bit, right? So this is 12, right? 1 1 0 0, because we don't have any sign, and this is 0 0 1, right? So we will be performing the addition by using 1's complement, right? So you can say that we have 1 1 0 0, right? And this is 1 after addition, so it has to move here because we don't have any carry, and this is the resultant 1101, right? So this is the subtraction by using 1's complement, right? So here we have so for negative number we will take the complement, right? So because here we don't have any negative number, right? So 0 1 1 0 0, right? And you can see we have -1, right? So we will be taking the complement, so this is the complement, right, of this one, right? So after the addition, this is the carry, and carry will move here, and we are having 1 0 0, right? So you can see that we have the 8 plus 2 plus 1, so this is 11, right? And this is the sign bit, that is plus. So if you solve it on the basis of decimal number system, so we will get the same 11, right? Right. So now let's talk about 2's complement, right? Addition, right? So here we have positive numbers, right? So you can see that we will be move on, right? So 1 1 0 0, this is 1, right? No carry, we will ignore the carry, right? So here carry will move here regarding 1's complement, but for 2's complement we will ignore the carry, right? Okay, now we have the sign bit, right? So sign number, so we will be having the sign bit, so we will complement this, right? And then we will add it, right? So you can see that we will be having, right? So we have to take the 2's complement of this, right? So I will be solving it over here. 4 zeros, 1, right? So 1 1 1 and plus 1. This is 1's complement, and after addition this is 2's complement, right? So this is 1 1 1 1 1, right? So now we have to add 1 1, right? 0, and carry will move here, so 1 1 0 plus 1 1, right? So carry will move here, 1 1 0, and this is the carry, and we have to ignore this carry, right? So 8 4 2 1, right? So this is 0, we have 11, right? So if we talk about in a decimal way, number system way, so you can have an idea that we will be having the same answer, right? So another example, right? So here we have 13, right, and 5. So what we need to do, we need to calculate the 2's complement of this number. So 5 is 0 1 0 1, right? So what we will be having, right? So 1 1 0 1 0, right? 1 1 1 0 1 1, right? So this is 1's complement, and this is after addition 2's complement, right? So this is now the sign number, 2's complement representation of the sign number, and we will be performing the addition, right? So 1 1 0, 1 carry, 1 1 0, 1 carry, 1 1 0, 1 carry, right? So 1 1 0 1 1 carry, 1 1 0, and we have, right? So this we have to ignore. So what is this? 8 4 2 1, so it is equal to 8. So that is, if we think in a decimal number system way, right? So this is the true answer, right? So here we have another example, right? So 2's complement. So this is the negative number, right? So we have to 1 1 0 0, right? So 1 0 0 1 1, right, so here we have this is 1's complement, right, 1 1 0 0 1 0 1 1 0 0 1, right, and after addition 0 1 carry 0 1 0 1, right. So now we have to add, this is 2's complement representation of minus 12, right, so we are having this, right, so as we have the sign bit is on, right, so I will be having 0 1 1 0, right, and 1 1 1 1 0, right, so this is equal to what, 7, right, 1 2 4, right, 7, because we have a sign bit here in the resultant, so that's why I have taken the complement again, and that represent the minus 7, right. So here I have a very generic mechanism of 1's complement representation, right, so you can see that we have a circle, so this is, and I have used 4 bits, right, but I have represented only from 0 to 7, and 1 bit is actually reserved for the sign, right. So here you can see we have zeros starting from 0 to 7, right, so mentioning this right hand side of the half circle includes positive numbers, so here we have all ones, right, in the most significant bit mentioning, so here, 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 right, but remember, although we talked about that we don't have a number system where we have plus 0 and minus 0, right, so by the way, this is not the number system, we just have to are looking for an easy way where we can straight away find 1's complement, right. So this is the representation, equivalent binary representation, and here we have the corresponding decimal with signs, binary representation, and the corresponding decimals with negative sign, right. So here you can see, if I want to calculate and know the 1's complement of 3, right, so for 3, right, so how I can do, I know that I have 0 1 1 and this is sign bit, right, so for 3 I have 1 1 0 0, right, so this is like this, right, and if I want to calculate the 1's complement of this, right, so I have 1 1 1 1, this is for sign bit, right, so I will be having this, right. If I want to know the 1's complement of 0 0 1, that is equal to plus 1, so 1 0 0 1 1, so 1 1 0, right, so 1 1 1, 3 1s and 0, right, so this is like this, plus 2 0 0 1 0, right, 1 1 0 1, right, for 4 I have 0 1 0 0, right, and 1's complement is 1 0 1 1, right, so 1 0 1 1, right, and for 5 0 1 0 1, right, so 1 0 1 0, right, 1 0 1 0. For 6 I have plus 6, right, 0 1 1 0, right, and I have 1 0 0 1, so I have this, right, so 0 1 1 1 1 0 0 0, right, so I have this, right? So you can see that we have horizontal lines. If I want to calculate the ones complement, so I can draw the straight line, right, horizontal line, and I will be having the direct value, right? I don't need to invert all the bits, right? So we can have this sort of circuitry, right? And then after ones complement, we should try to look for a mechanism so that we can calculate twos complement, right? So this is the same stuff, right? So here you can see 0 to 7, right? And here we have -1, -2, -3, -4 till -8, right? If I divide this circle, right? So how I can do that, right? So if I want to calculate or compute the, so here for example I want to take twos complement of this, right? So here 1 1 1 0, this is ones complement, right? So this is 1, right? So if I plot here, so this is again the same, right? So right, and this is ones complement plus 1 1 1 1 1, right? 0 0 0 1, right? Right, so you can find something very interesting, right? So if I move one bit position to the clockwise direction, right? So this is the clockwise direction, so I will be having this, right? So this is twos complement of plus 1, right? So similarly, if I take, let's say, plus 3, that is 0 0 1 1 1 1 0 0, right? So 1 1 0 0, so plus 1 1 0 1 1. So here this is the same straight line, and if I move here, so this is 1 1 0 1, so that is the twos complement. So straight line, and then I will flip or move the needle, right, from one number to the next number, and that is the desired complement, which is twos complement, right? So if I take this, right, 0 1 1 1, that is plus 7, right? So here 1 0 0 0, right, 1 0 0 1, right? So here you can see this is 1 0 0 0, ones complement, right? And I have to move here one bit position towards the clockwise direction, so 1 0 0 1. So that is, so here what we have, right? So instead of doing all this stuff, we can simply have the sort of mechanism where we draw the straight line. For example, if I want to have the twos complement of this 4 plus 4, right? So this is 1 0 1 1, right? And then I will move one position upward, and this is the required result, right? Right. And this is the same, almost the same circle stuff, but whenever we talk about the overflow, right? So you can have an idea, right? So here we have, right? So you can see if I want to have, right? So this is 0 1 2 3 4 5 6 7, right? And here we have the negative number, right? So you can see here we have all zeros, right? And here we have all ones. So it means these are the negative numbers on the left hand side of this circle, and here we have the positive numbers on the right hand side of this circle, right? So this is the difference, right? And if I will cut down, right, this from here, right, so these are the negative numbers, right? So you can see that I have to cut from here, right? So then this will represent, right? So here you can see that we have 0, right? So this is the 0, and right, so this is 0, right? So let's talk about 0 0 0 0, right? 1 1 1 1, 1's complement 1 is 0, 1 carry 0, 1 carry 0, right? 1 carry 0, and here we have 1, right? So, right? So we have 0, right? And -1, -2, these are the negative numbers, right? And here we have the 0, right? So this is 2's complement number system. Here we have positive numbers, right? So if I go back, right, so this is a very unique sort of mechanism in order to have the 2's complement, right? Right, so let's summarize today's lecture, right? So today we have more number system, because in the last lecture we have not discussed hexadecimal numbers, right? So we discussed in more details hexadecimal numbers, and we also have taken a lot of examples regarding the interconversion, and we can also now have an idea that there are a lot of different ways that can be used in order to accomplish the interconversion from hexadecimal to octal, right? And from octal to hexadecimal, and from hexadecimal to decimal, right? And from hexadecimal to binary, and so on and so forth, right? So we have performed a lot of examples in order to have a very strong grip on this number system, because this number system will ultimately help us in order to proceed further for that course, right? So I wish that you will perform a lot of different examples by yourself, right? And you will be having hands-on experience regarding the number system interconversion, right? So you can take examples, and you can convert first, because we have gone through two sort of mechanisms. In the first mechanism, we suppose that our circuitry or our system is based on the number 2 base system, right? Or it is designed on the basis of binary number system, right? So in that case, right, we have the binary number system as the native number system, and what we need whenever we are trying to convert or move from one number system to another number system, what we need to do, we have to first convert from one number system to the base, that is the native number system, binary number system, and then in the second go, in the second step, we have to convert from the base 2 number system to the targeted number system, right? So this is the one way of doing the job, and in another way we can always convert from one number system to another number system, right, straight away. Like you can go from hexadecimal to decimal, from hexadecimal to binary, right, from hexadecimal to octal, and so on and so forth, and you can say vice versa, right? So we talked about a lot, and we have done a lot of examples regarding the interconversion between different number systems. Then whenever you think about the computer system, right, or the number system, or the operations that has to be performed, so you come across signed number representation, right? So there are very easy ways to handle and manipulate those signed numbers. Like I have given an example that whenever we have to represent a signed number on a piece of paper, what we normally do, we put a bar on the side of that number, and that indicates the negative number, right? But in case of computer, we cannot do like that, right? So we have to manipulate, we have to handle in a systematic way, right? So we have different mechanisms, right? So first we discussed the ones complement, right? And then we talked about twos complement, right? So whenever we want to represent a negative number, we take the twos complement of that negative number. So instead of performing the subtraction, right? So what we normally do, we add the two numbers. First, for example, we have two numbers, A, that is positive number, and another number, B, that is a negative number. So we in effect has to perform the subtraction. But what we normally do, we take the twos complement of the second number, B, that is negative, right? So now instead of taking the subtraction or taking the difference, we will be adding the two numbers, right? So first number will remain as it is, the second number is the twos complement, right? So there are different mechanisms, right? So we can perform addition by using one complement, right? We can also perform subtraction by using ones complement, right? So we can also have addition by using twos complement. Similarly, we can also perform subtraction by using twos complement, right? So we have discussed twos complement and ones complement, and then we have performed addition and subtraction by using those different complements, and we have also justified that why we need to complement, right? So we can also have the complement of another base system, as we have mentioned regarding the decimal number system by taking the example of the odometer, and we have justified that why we need the complement of a number, right? And finally, we have devised a very short and very precise method of taking the twos complement, right? So you don't have to invert the bits, you don't have to add one, so you just have a sort of mechanism, right? And you all the numbers and their complements are written in the form of a circle or around a circle, right? And you just draw the straight line, right? So in case of ones complement, we have the horizontal lines, right? And we just draw the corresponding horizontal line, and the numbers that are in front of each other from regarding head to head, they represent complement, right? So for example, if we have number on the right hand side and we draw the straight line, and we have another number on the left hand side of that circle, right? Remember, the line should be horizontal, right? So in that case, we will be having the ones complement, right? So regarding the twos complement, we will be performing the same first step, right? But we need to do or perform an additional step, right? We have to flip the knob, that is circle knob, right, one digit position towards the clockwise direction, right? So that's all, और मेरी तरफ से अल्लाह हाफिज़, अस्सलाम वालेकुम।